Okay. Yeah. So I think you can start
Yes,
from
we
the
can
beginning.
start.
It, uh, huh?
Almost 50. It's already 50, so we can start.
Yeah. Yeah. So the
Yes.
whatever you wanted to say about Nayak ji, you can keep it reserved for towards the end.
That I hope he will be able to join before I get. Okay.
Yeah. So
Should I go to
welcome.
presentation?
Welcome. Uh, Welcome to the third session, the third day session of the webinar series. And as usual, we have three speakers today. And first speaker is Professor Moitreyi Saha Sarkar, and she's a good friend of Dr. B.K. Naik, and they are almost contemporary. And let me brief a little bit about her. That Professor Saha Sarkar completed her PhD from Saha Institute of Nuclear Physics in 1994 and joined the same institute as faculty member in 1996. Her research interest includes experimental nuclear astrophysics, high-speed spectroscopy, nuclear structure, and others. So today she will be talking on relevance of nuclear structure in nuclear astrophysics. So please, I'd request now Professor Sarkar to start her presentation. Yeah, you can start presenting.
Okay. Okay. So can you see these slides? Can
Yes, yes,
okay.
yes, it is. Yes, we
So
can.
I thank the organizers for giving me this opportunity to speak on the occasion of 60th birthday of on my exactly my contemporary. So maybe a few words which I wish to tell about him. Maybe I can tell at the end. So I will be speaking on the relevance of nuclear structure in nuclear acid. So Indranil has made my life very easy because he has spoken a lot about the basics of nuclear astrophysics. And as a nuclear physicist, how can we contribute in information which is relevant for nuclear astrophysics scenarios? But few one or two slides I have kept for just continuity. So primarily, we from nuclear physics inputs, we would have to provide data to the astrophysicists so that they can understand about the stellar objects and they can also know about the nucleosynthesis of different elements. So in the present talk, I will be talking about two different regions of masses where we have worked, either in the theoretical frontier or in the experimental scenario. The first part is somewhere in the CNO cycle region, and in the other case, in the second case, the explosive scenario where rapid neutron capture process is involved. Now, as everybody knows that for nuclear astrophysics reaction rate measurements, there are a lot of experimental difficulties. And as the cross sections in the relevant region of interest are very low, one has to be very careful about effects which are not of that significant effect for normal nuclear physics experiments. For example, the background level, the natural activity, the beam impurity, the target impurity, everything can create a havoc if we are not careful. So, compared to the normal nuclear physics experiments which we do routinely for in our high school spectroscopy or in nuclear reaction, it's somewhat very different, and we have to be careful about very small details of the things. So there are quite a few experimental challenges. The first one is the low energy high current accelerator, and if you all of you must be knowing, and will also showed about our Frena accelerator, which was specifically designed to work in these problems because it is a low energy but very high current accelerator, and this is the only one of its kind in the country. We hope by a few months it will really start delivering things. So they have already tasted, and unfortunately due to lockdown, all things got delayed. And next, you need targets of extremely high purity and stability, unlike in the nucleophilic cases. Here, as the beam current is quite high, in some cases you may also use milliampere currents. Targets have to be very stable, and you have to keep the purity of the stuff. Targets very high. The background level for gamma background, especially I'm talking about, has to be reduced a lot. I will be talking in more details later. And you have to think of new interesting techniques, some innovative techniques to get rid of many of the problems. And the interesting problem for these nuclear astrophysics experiment is each experiment is a challenge. So there is no universal solution for all the experiments. So you have to know about the special problems of each experiment. So in the world also, in different accelerator centers, people are concentrating each accelerator center on specific few reactions, and they are tailor making their accessories, their analysis techniques, their detector sets to address only those problems. It's not that like in high speed spectroscopy and other things that you have a setup and you can address all the mass regions whatever you wish to address. So while talking about these solutions to experiments, I will be talking about some of our efforts. In some cases, I will be talking in the first part of my talk, I will be talking about some incidental detector developments, targets, preparation, some suppression of background levels, some analysis techniques, and finally a very specific experiment which we did to address a very important reaction in nuclear astrophysics. And on the theoretical front, I will first talk about some shell model calculations which we did to explain some reaction data which we got from the experiment I mentioned. And in the other case, I will be talking about some theoretical endeavors which is very important for unprocessed nuclear synthesis. So the first thing which I mentioned about is the purity of the targets. And for nuclear astrophysics, implanted target is a very well-known thing which people use because you can have very isotopically pure targets and which can withstand high current. So we have started working on these type of targets since 2008, and this endeavor started following a discussion with Professor Michael Vischer and Professor Joaquin Juarez of Notre Dame University, USA. And we prepared quite a lot of implanted targets within these stages. So to give, because I will not be talking much about these implanted targets, I will be showing use of it. Just in this slide, you can see how many targets we have made. And you can see the first target which we attempted was made in Kolkata Shah Institute isotope separator, which is presently not working, but at that point it was working, and however it had some problems, so we could not continue with that. However, we got the first target in using that reaction. Later we did the three targets of nitrogen as well as neon in TIFR using the ECR so small low energy accelerator in Lokesh Trivedi's lab. Finally, these oxygen 16 and 24 magnesium implanted targets were made at low energy negative ion implanter facility at USC. These targets are yet to be used. We have not finally used in real experiments here. And there are some publications, our communications, just to show the continuity of the effort which we are taking since 2008 or so. Because these are not like normal targets. Each target is a challenge, and you have to after working on the target, you have to, after preparation, characterization also takes a lot of effort. And thankfully I got support from not only people from our institute, in other departments of our institute, especially from the Quantum group, as well as throughout the India. I got people to help me and my group preparing these targets, characterizing them. While working on this, we have my student Swati Sharma. She presented this work in recent school, assembly school in Italy, and it got published in this EPJ Weber conference paper. Here you can see that when we prepare a target, we have to calculate it and we have to understand the thickness. We have to use another beam and use a resonance reaction to see the thickness of the target. And interestingly, we have seen, and not only us, other people have also observed that normal stream simulations sometimes cannot reproduce the data. In that work, in this work which I am showing here, we have seen that another implanter calculator, SASTRI, which is developed by it has got given us much better result compared to stream at this lower levels. Now we will be coming to our work, which is also recently communicated on background suppression. So background suppression means I am talking about primarily background gamma radiation suppression. So background gamma radiation, you all know that it comes from natural sources, from the cosmic rays, and from the sources on the earth, like for a long-lived radioactive nuclei like potassium-14, radium series, thorium series, and there are some very small amount of it also comes from some man-made sources like what cesium, etc., which is very small. While working for nuclear acidic experiments with that high current, there may be beam-induced background also, which may arise from beam impurity, maybe some impurity in the target, or maybe some problem with which can where we can hit some unwanted objects. And the other very important thing is the intrinsic background of the detector itself. So here regarding suppression of background, I will be primarily talking about this background coming from the natural environment, environmental radioactivity, and the radioactivity coming from the intrinsic background of the detector. So what we have done recently, we have measured and simulated the gamma ray background in our Fresnel accelerator. What we did, this is the schematic diagram of the Fresnel accelerator hall and the beam hall. We took the HPG detector and placed it in 4 different places in the beam hall and accelerator hall. This accelerator facility is surrounded by 1200 meter thick wall, and that's why we were also it can affect the data in 2 ways. One way, it can shield it from the outer environment. It can shield the inside activities from going to outside environment. It can also prevent outside activity to come for coming inside. However, we were worried whether this concrete wall itself can be acting as a source of radioactivity or natural radioactivity. So we wanted to take data in 4 positions before the accelerator was installed. It was taken. We have communicated. We have reported the initial results in 2018. So at that time, the accelerator was not installed. It was empty hall. And we also compared this active radioactivity with labs in our main building. One is the gamma lab, routinely gamma spectroscopy measurements are being pursued, and there is a lead box where we keep our resources. And we also took the data in some other room where the activity is relatively less. So we compared these 3 measurement values. And we found that in the accelerator wall, the gamma ray background is really much less than that which we saw in lab 1 and lab 2. As I already mentioned, that lab 1 is a standard gamma spectroscopy lab where you keep the sources, so naturally activity is much higher there. However, this accelerator hall has quite a less amount of radioactivity compared to the lab 1 and lab 2. So why is that so? Because we were thinking that the thick concrete walls will also give rise to some radiation. So here my student Shakib, she pursued some GR4 calculations, some simulations. She did a very toy thing, and she took this type of a geometry where she took a circular concrete sheet and distributed the radium and thorium series radioactive nuclei uniformly in the sheet in this concrete wall and placed the detector in the middle of the sample. Then she found what happens when you increase the thickness of this concrete wall. Interestingly, we found that as you increase the thickness of the wall, as the amount of radioactivity increases, the photo peak gradually increases, which is expected because the amount of radioactivity is low, because you are distributing the radioactive material in the concrete wall. But as after some time, when you go to certain thickness, after 25 centimeter, you will see that it almost saturates. That after that, there is no further increase in the radioactivity measurement, and it almost saturates. Why is that so? You can understand it very easily because when beyond 25 centimeter, because the highest energy gamma ray which is in the environment is 6.5 kV, it gets the 3 MeV gamma ray which is coming from beyond 25 centimeter, it is getting absorbed inside. And as expected, the compound part increases. As you increase the thickness of the wall, the compound part increases. However, the photo peak saturates. So this is an interesting observation we found. Later, we also worked on the same case. We worked with the same detector and put it inside some active shield and some passive shield, a lead box with all sorts of small lead bricks and braided shielding to see how much suppression we can go for. Moreover, we also put the detector inside a large sodium iodide SAM spectrometer. This is a very old detector which was lying in a corner in our department because this is a huge detector and it was almost, the data counted is abnormally high and it's very difficult to manage. So we started working with it again because now with Frena this detector can be excellent. So this is for passive shielding. First we put the detector. This is a detector, HPG detector. You can see this is a long neck detector. There is a bore hole inside this detector assembly. So we have pushed the detector inside the bore hole, and we found that it acts as an excellent passive shielding. And we also did some anti-coincidence setup with this. So these act as a anti-counter shield and also anti-room background. And you can see the result. This is the environmental background without any shielding. Now we have put the detector inside the SAM spectrometer, this red curve, which definitely decreases. Then, as this is a long bore hole, so there were some gaps. So we have plugged in small lead bricks to close those, and we found it has decreased quite a lot. And then we have also used electronics anti-coincidence circuit to use the shield, the SAM spectrometer as a shield, as an active shield, and we found further improvement. So this was so we expect that if we can move that SAM spectrometer in the accelerator hall, we can reduce the gamma ray background multiple folds. And as primarily this accelerator is meant for measuring heavy ion fusions, that is carbon-12 carbon-2 type of reactions, where most of the gamma rays will be less than. So instead of going underground, this type of shielding arrangements with this concrete shielding elements will be very helpful for measurement of these reactions where the gamma ray energies are less than 3 MeV. Next, I show you some results where we have worked on some backgrounds which are coming from the detector's brain cells and how to get rid of it. This is one of the very old work which we did in 2007, where by chance we found that this the VGO shield in which we have put our detector for suppression, we found that is also giving rise to some long-lived 207 bismuth activity. So we reported it in 2007, and this was one of the we are very much amazed to see that the shield itself was a source of radiation. And the next thing which I want to show is the very recent work done with Dipayan. One of your students who has done his PhD from ERC with Shankar. Dipayan and our people, we have worked together to see the how to eliminate the internal activity in lanthanum halide detectors. We got a lanthanum chloride detector from one of our colleagues, and these lanthanum chloride detectors, lanthanum halide detectors, although they are excellent energy resolution, and their timing resolution is also very good, they have a very bad problem. They have a lot of internal activity. Where does this internal activity come from? You can see it here, because 139 lanthanum is the stable isotope of lanthanum. However, there is 138 lanthanum and has 0.09% abundance, and it has a half-life of 10 to 11 years. But this is a radioactive nucleus, and it can decay by two ways. One is by electron transfer, 6%, and another is by beta decay, 33%. So you can see the gamma rays coming 789 keV coming from the beta decay, and there is a 1436 keV coming from the electron capture. And with the beta decay, you have a beta continuum. Moreover, these lanthanum and actinium are in the similar chemical properties. So in lanthanum detectors, most of the time you find actinium radioactivity. And the longest lived actinium isotope is 227 actinium, which has a 21-year half-life. And you have a series of alpha decays, alpha and beta decays, and all these as those alphas are detected by the detector, and as alphas energy loss is different from gammas, almost 4-5 MeV alphas give their energy peaks in the gamma spectrum at 2 to 3 MeV. You can see these bumps. These are from the alpha contamination in the detector. So how to get rid of this? If your intrinsic gamma background is so much, how can you see weak peaks, especially for these capture reactions and all? So what we did, we used a digitizer. Some people have already used, and we also did it in a different way. We used a KIAM 5730 digitizer and found that the alpha waveforms and the gamma waveforms are quite different. You can see the gamma waveforms are quite wide, whereas the alphas are sharper. So if you define you set short gate and long gate and define a pulse shape discrimination parameter, and you can find there are two definite bunches of alphas and gammas. You can see a nice demonstration of it, because you see this is a 207 Bismarck spectrum we have taken, and you see that in the raw spectrum this 1770 peak cannot be seen due to these alpha contaminated peaks. However, after you select gamma part from the PSD spectrum and project the spectrum, you see the alpha is totally gone, and this 1770 peak comes up very nicely. However, this beta part is still remaining there. So, for removing the beta, Deepayan has done GEOS simulation, and the beta activity by calculating the activity of lanthanum, 138 lanthanum, depending on the abundance ratio, etc. He has simulated the beta activity of the detector. So finally, what we did is that first we eliminated from the background the alpha contamination from PSD selection. Next, we have used this simulated beta activity and normalized it with the activity in the detector, and then subtracted it. Finally, we got a spectrum which is like this magenta color spectrum, and you can see this 1435 part is gone. Only the 1416 now is standing, and the 2615 has also come out because you have eliminated that. So that way we can demonstrate that if you use this type of technique, you can get rid of this intrinsic radioactivity of lanthanum chloride or lanthanum bromide, and you can utilize these detectors to its best. We have also worked on some innovative techniques for studying long-lived isotopes and decay, radioactive buildup and decay with single timestamp data. It was done as a part of the thesis of my student Shongita Das. What we did, because in nuclear astrophysics many times you do activation analysis, and for activation analysis you prepare targets, you irradiate targets, you prepare some radioactive species and follow its decay. But for normal cases, what we do, we take data in some equal time pills, say 10 minutes each or 5 minutes each, and then finally draw the decay curve. But here, what we have done, we have taken continuous continuous data with a digitizer which provides you timestamp also. So instead of having equal timings, we put equal number of events because here we are acquiring data by its timestamp. So for example, here we have used a 5780 digitizer, and instead of equal timings, we have taken 20,000 events for each cell, and that way you can and for the time difference we have taken the first timestamp and the last timestamp difference of time. So that way instead of having equal time windows, we have variable time windows, but the number of events is same. So one way it is good because usually for decay studies, what happens when you keep the time window same, at the end of the decay, the error bars gradually increases. But here, as you are keeping the time number of events same, the statistical error from that number of events doesn't change. However, the time window increases. So after doing this, we have shown that in this way, as you are taking continuous data from the same set of data, you can very well determine a 2 minute to hours order of data without changing anything. Moreover, while taking the data, we also did another interesting observation we found. We also took the data, we continuously when the beam was on, and we didn't stop the data, and we allowed the data to go on, and we found that so this plot you can see as a function of time we have plotted the counts, and we found that when the beam was on, these are in beam gamma rays, and when the beam stopped suddenly, these always reduce to zero, but there are few, if you look at it very carefully, there are few which has very short half-lives which started decaying. So for by this, what we could do that for very short half-lives, which is difficult to take out from the, you need some rabbit or some William jet to measure those half-lives. Instead of that, if you take the data in this continuous fashion in timestamp, you don't have to have any mechanical device like that. So a very short half-lives also you can measure, but you take the data continuously, beam on and then beam off. So depending on, because my timestamp, this time window was 10 nanoseconds because this is a 100 megasample digitizer. So you can take your time window as small or big as you wish. In that way, we demonstrated that from day to minutes, we could see that we didn't have any shorter half-life in our experiment, so we could not demonstrate. Now, with all these experimental techniques and detector characterizations, we finally come to the point where we really go for an experiment which will be useful for nuclear astrophys. So, this is the method where gamma spectroscopy methods will be used with implanted targets. What we study? So, we will study the resonance reaction. Because resonance reactions are very important. People know that when you extrapolate the data to lower energies, these resonances are really problematic, and if you do not get them, this extrapolation can fail drastically. So the resonance contribution sits on the top of the direct capture cross sections. So what we have done, there is some particle for is incident on a target. So if the S1 is the separation energy of this limits of this particle number 1, then beyond this the levels will be unbound. So there you can see some states which has finite width, which can stay for some time, some longer time. So these states can be called as resonances. And in many cases, it happens that these states either can decay through these because this is above the separation energy. So there will be definitely a decay channel for particle, as well as there will be gamma. In many cases, there are evidences where gamma channel is the most dominant. And you can understand from the Wigner line shape and this uncertainty, if you know the delta T, that is the time of the state, lifetime of the state, you can determine the energy width of the state like this. So to give you an estimate, just because how much is the corresponding lifetime? Say for when the width of the state is very small, the associated lifetime is of femtosecond. And if it is gradually increases, it is much smaller. So for these cases, you can scan your energy to trace the resonance. For these cases, you cannot scan your energy to follow the resonance speed, but you have to measure the lifetime of the speed. So these resonance reactions we had used long back in 2006 for these carbon 13 P gamma as well as 27 aluminum P gamma for characterizing some detectors. And these cases you can see another interesting thing, as these reactions are very high, large positive Q value reactions. With putting only 3 MeV beam energy, you can get 10 MeV, 12 MeV gammas because the Q values are constant. So that way we characterized Grover detector long back in 2006 using these resonance reactions, because that gives rise to 11 MeV gammas, and we characterized that detector still Grover detector still 11 MeV using such resonance reactions. But now I will be talking about the specific nuclear reaction which we have recently completed and communicated, is the study of a proton capture resonance state of oxygen 15 at 7556 K. So this reaction is a very important reaction. It is the highest Coulomb barrier it has in the CNO cycle 1. So it is the bottleneck of the reaction. So it's very much important in astrophysics. And this reaction, you can see, this is the separation energy 14 nitrogen plus P, oxygen 15. This is the level scheme, and this is the separation energy value. This is the Q value of the reaction 7297 keV. And above that there are resonance states at 259, 987, and 2187 center of mass and energy. However, if you have seen, there is a sub-threshold resonance, that is 6791 keV, which is below the Q value. So which is half threshold, which is also very important when people are going to extrapolate this cross-section data to zero energy. This 6792 keV, which is a half threshold resonance, has a very strong influence. So with that is in turn the lifetime of this state has to be measured very accurately. And you can see in 2013, this is from a thesis I have taken. There are so many measurements done over a long period of time, and there are lots of uncertainty. And very recently, also, a lot of people are trying to study these reactions. And even in 2018, there has been a publication where they have used activation method to use this. And there are more measurements still needed because this value is still very uncertain, and that is we have to determine the width of this level. That is, we will measure the lifetime of the state, and this level actually decays with almost 100% probability by addition of gamma rays. So we can get the total radiation by measuring the lifetime of the state. And this level, as I have already told, as the width is very small, the lifetimes are in the range 1 to 10 to 10%. So we can go for Doppler-Schick attenuation technique for the measurement. It has been seen that people are using kinematics reactions like what we have done, as well as the inverse kinematic reactions. Because it is easier, you go to higher energies and your recoil velocity is high, so your Doppler shift or broadening is much more, so you get more reliable data. However, it is found that when you are getting data from this method, your result doesn't agree well with the matrix. So there is some controversy. Why is that so? And here nuclear structure also comes in a big way, because nitrogen 15 analogous state can be scaled, and its half-life is 0.61 femtosecond. So it is expected that oxygen 15 half-life will also, that is 792 keV, will be also in the same. So we have studied these particular 7556 keV resonance state populated by using proton energy 270 keV lab energy, and then which decays to this 6792 keV, whose half-life we have measured. The reaction, the experiment has been done. The experiment has been done at TIFR, ECR lab, and this target which we have used, we have done RBS measurement at IUSC to exactly see what is the composition of the target and the stoichiometry, and we found this is the stoichiometry. We did the experiment at Professor Lokesh Trivedi's lab in TIFR, and the beam energy was scanned from 278 to 350 beam KV, beam current was 2 to 4 microampere. We have used, this is the beam line you can see. This is the HPG detector. This is electrically cooled HPG detector, and this is a sodium iodide detector. This is the same. And you can see this is the target frame. This is the end flange we have put the target on. And unfortunately, for this, the beam was not exactly at the center. It was fell on the target at one edge. So, and the data you can look at, and you can see there is an excellent shift. Although that you can understand at 270 kV the velocity is very low, but however, as the gamma index is very high, and the half life is very small, you see shift. 184 kV is the strongest gamma, and you can, if you look at this 1460, these two angles, you do not see any shift in the peak. However, these peaks are shifted, so which indicates that this is not due to any amplifier, rate shift, etc. This is due to this lifetime of the shift. This is 6172 kV and this is 6792 kV, and you see very excellent shift in the peaks. Now we had to simulate because we have to go for simulation. Why is that so? Because I told we put the target in the end flange, and the beam positioner was shifted from the where we put the radioactive source. Moreover, the end flange there was it had a collar, so efficiency also when you put on the sides there are shadows coming from these edges, and the experimental data has to be properly taken care of for the attenuation and other things, because our radioactive source position and the beam position was not exactly same. So we did extensive simulation for characterization of this electrically cooled BEG detector in 7 and 8, and it is already published in Nuclear Instruments and Methods. From there we got the absolute efficiency from experimental, and we also simulated and found very good agreement. We also look for these escape peaks and how it changes with the size of the detectors and different parameters we have checked. So after we have got those efficiency information for the detector confidently, then we went to extract the real physical important physics from the data. From the scanning data, we got the yield curve analysis, we got the yield versus photon energy plot, and we found that the target thickness is 21 plus minus 1 keV. This is energy because we are varying energy of the photon because this resonance state 7556, its width is 0.99 keV, 0.99, that is almost nearly 1 keV. So we have scanned the energy to see the profile of implanted nitrogen in the tantalum battery. And from there we got the resonance strength, which agrees very well with the earlier results. Then we went to the lifetime measurement thing, and you can see for different angles the shift is very prominent and nice. But the problem is that here, as the energy of the proton is very low, that means 278 kV, the required oxygen has a required energy of 20 kV or so. And you know, people who are working in nuclear structure and lifetime determination, at these low energy, nuclear stopping plays a very important role. However, we do not have enough data, and she is also not that confident of prediction at these low energies, where you can see that nuclear stopping competes with the electronic stopping, which we detect at higher energies. However, with that only we have to proceed because we do not have any other way. So from there we got the gamma rays which are coming out from the 7556 kV state, because this is a very narrow width state, so the lifetime of the state is very small. So here you will not see any shift because there will be no f tau value, because there will be no velocity at emission. There will be shift, but the velocity will be exactly same as the initial velocity. So for that case, we take f tau equal to 1. So from there we fitted the plot for different angles and got this beta 0 p value from here. And with this beta 0 p value, we got the f tau value for 6792 kV. Now, and this f tau versus tau plot we have generated with, that is a big story. I cannot go to detail of that. That we have generated, simulated the particle trajectories and their velocities and function time. And then the velocity beta t we have fitted with some polynomial, and then from there we have generated the f tau values. theoretical F-term values as a function of tau, and then from there we have put our experimental F-terms to get the tau values. Unfortunately, as also seen by other people, we found that our F-tau value for corresponding to 6792 keV is almost at the limit, and so we cannot get a definite value. For 581 keV state, we could get a value which is finite, but 6792 keV we could probably give a limit. Now we went to shell model calculations because these states, how much it will be populated and the radiation, this capture resonance strength will depend on the spectroscopic factor of the states, which is a very important input. So nowadays, although a lot of experiments are being done, not many shell model calculations and spectroscopic factor calculations are being done.
Professor
So we
Sarkar,
did just 5 minutes. Can I go for 5 minutes?
Okay.
So we did a shell model calculations. We got very good results. We also calculated the spectroscopic factors, and I cannot go into more details. There are some issues. There are scope for improvements, and we also are thinking of possibility of predicting weaker resonance. If we do good shell model calculation from the spectroscopic factor calculations, we can also predict weaker resonance, which can be expected. And this is the final part. Just slides I will show. This is because we are also working in 132 team region, which is purely experimental theoretical work. We have generated a new cross-shell interaction in the WMF for relevant for 132 team and its neighbors. This is also part of the thesis of my student Shomika Dash. And these cross-shell excitations are very important, especially for nucleus which are exactly at the shell closure or just one or two nuclei beyond it. And we have found that for many cases these nuclei has U1 transitions. So U1 transition means you have to have orbits which is different by delta L equal to 1 and changes factor, which is not existing the existing interactions, which is very popular in these nuclei. So we have generated new interaction by coupling two standard interactions of this region, and generated a new interaction and calculated the spectroscopy properties for several process nucleosynthesis relevant nuclei, and we got very good agreement with the data, and we could exactly predict the states which are excited due to cross-shell excitation, which was not could not be done earlier. So this is all, and this is our team and my collaborators. There will be some other people because we are working for so long. There are a lot of more people. I may have forgotten to write. I have missed them. I'm sorry for those names which I missed. And I also thank you for giving me this opportunity to talk on the occasion of Nayak's graduation. And I hope you will have a long active life. Future, and he's very encouraging. He always looks for new. He's very positive in his approach. That I always appreciated from my young days when we met in one of the SARS books. So I wish you a very happy life. Thank you. Hello, I have done.
Thank you, Professor Sarkar, for such an excellent talk and giving whatever all the information that steps you are taking towards the nuclear astrophysics studies, and which will be very relevant to upcoming facility training. So thank you very much. And now the session is open for discussion. So I request the audience, they can unmute and ask the question one by one.
Hello, can I ask? I'm Ramchandra from BRC.
Yes, go ahead.
Yeah. So in this, your initially, you showed about the background. So cosmic background, does it bother you in any way?
No, for our cases, this concrete wall shielding helps us a lot. And as we are only interested to gamma region, which is below 3 MeV, even if you go down, you are below 3 MeV, this natural radioactivity is the most dangerous thing. So if you have gamma analysis beyond 3 MeV at higher energies, then cosmic background suppression is a very big issue. For our case, it is not that big issue because here the natural background overrules this cosmic background.
Okay, thank you.
Any other question?
Yeah, can I ask one question to
Yes.
Definitely.
this R.K. Chaudhary here?
Yes, yes.
Yeah, it is nice to see a lot of preparation work about the capture reaction studies where you are also quite expert in this field. And I think when the facility comes up, you are almost ready to do the measurements. I just wanted to curious to know, are there any preparation similar thing going on for charge particle channels? Say for example, I had one question, but whether you can answer or not. Magnesium target which you are going to prepare with implantation. If one does alpha P reaction, it goes to aluminum 27, and if you can also implant aluminum 27 into P alpha, it goes to silicon 28. These are the very abundant isotopes inside in the synthesis process. Whether some of these type of studies have been already carried out, or what is the literature, I am not fully aware. But whether some plans in these directions for all charge particle reactions is being done.
For the charge particle, Chinmoy Boshu is planning a scattering chamber, and already it was for this, there was some dearth of fund. So now the situation is a problematic now because there is a big chamber he has planned, and already it was almost going for fabrication. And there are small existing chambers which they are trying to replace for the initial set of experiments. And for this magnesium implanted targets, the problem is that most of the cases the backings are quite thick. For implantation here, there is a carbon backing, and for magnesium we have already done this capture reaction with some evaporated targets. And this type of thing which we are telling about this alpha P and other reactions, that I am not really aware. I am not aware. Maybe should be without maybe.
Yeah, but implanted targets, one can look at the charge particle on the side of the target, not on the backing side.
No, but we have this magnesium. Magnesium target has a carbon backing, so that is not that bad. So that
Okay.
also one can try and see.
Okay.
And unfortunately, I am retiring in September, so I no longer there to work with Frena. So that is also.
Finally, when are you going to operate Frena?
Frena was almost at the because these people who came for installation, they needed another week, one week more for the installation. Then suddenly they were called back to their country before this lockdown. So I do not know now. I'm not very sure what. Because they already tested heavy and I think alpha proton is also done. Only alpha was remaining. But,
okay, thank you.
Any other question? If not, then let us thank the speaker once again for her excellent talk, and we'll go over to the next talk. So next talk is by Professor Marco Sinacero, and
Hi.
he's hello.
Hello.
Yes.
Yeah, okay.
Yeah. So let me introduce by
Yeah,
saying a few
okay.
words. So Professor Marco has completed his master's degree in 1991, and the thesis titled "Study of the Excitation Energy Dependence of the Level Density Parameter in Nuclei with Mass Number A equal to 40." He has been associated with INFN from 1992, responsible of the 8 pi light charge particle spectrometer and Ripon modular array for neutron spectroscopy at LNL. He has published more than 200 papers in the peer-reviewed international journals. He is referee of several INFN projects and member of several organizing committees of international conferences. And he has been the collaborator of the NPD BRC group and INFN, and he is one of the best friends of Dr. B.K. Naik. And today he has kindly agreed to talk on the study of the competition between non-equilibrium processes and fusion evaporation in heavy ion reactions, an experimental method to investigate clustering in nuclei. So may I now request Professor Marco to start his presentation.
Okay, thank you. Can you hear me?
Yes, we can.
Okay. Okay. So, okay, can you see my
No, not yet. Yeah, it started. It started. Yes,
Okay.
it has come. It has come now.
Okay, good. So first of all, let me thank the organizer to give me the opportunity to speak here in this contemporary topics in nuclear physics, and in particular because it's the occasion of the birthday of our friend Nayak. We have a very long standing collaboration between the BRC group and INFN and the University of Padova. And so I'm very happy to be here. Coming to my presentation, this is a kind of, let's say, update of what I presented 2 years ago in Mumbai in the workshop, nice workshop organized by my friend Indranil Mazumdar. And I will talk about the possibility to investigate the clustering in nuclei, studying the competition, so the process in non-equilibrium processes and also the fusion evaporation in heavy ion reaction. First of all, let me outline my talk. First of all, just a small introduction of the Legnaro National Laboratory in the nuclear physics landscape for those who doesn't know the laboratory. So then I will talk very briefly on the cluster, on the structures in nuclei, some basic concepts and possible signature in heavy ion reaction dynamics. And then I will talk about the NUCLEX experimental campaign at LNL on light and medium mass nuclei. So I will draw some perspective with radioactive beams, with especially delivered by our upcoming facility space. And I will try to draw some conclusions and maybe some questions. Okay, so Legnaro is nearby Venice and Padua in the northern part of Italy. As you can see, is in the center of Europe and is well connected with other large-scale laboratory in Europe, like Ganil, like ELIANT, GSI, and we are part of this European network called Eurons, then ENSAR, and then N2. And we have also, within this consortium, signed a lot of MOU with many labs in the world, and in particular also with the TFR of Mumbai. So this is a brief overview of the accelerators and equipments that we have in Legnaro. The first one is the Tandem XTU, is a 16 megavolt machine installed in the 1980. So the first large scale, the first big accelerator in Legnaro. And after 10 years, more or less, we installed also a LINAC accelerator called ALPI, and then a ACR ion source injector in 2004 for injecting other kind of beams that cannot be cannot be delivered with the tandem XTU. And then we have different experimental equipments. I would like to cite Exotic for the production of light radioactive nuclei, the Prisma spectrometer for the study of direct reaction of multi-nucleon transfer reaction. And now we have the Galileo array, that is let's say the hair of GASP, and also the local gamma array, while Agatha is the traveling array of Europe. And in the next year, we will host again this array, and then the Garfield array for charged particles, and this is the main detector we use up to now. My group use up to now, and I will describe and I will tell about the experimental campaign in this accelerator. And then we have also two small accelerator, Van de Graaff of 2 megavolts and 7 megavolts, mainly devoted to interdisciplinary physics, but also devoted to some astrophysical measurements. I mentioned the perspective of the radioactive beam. We are building a radioactive beam facility, SPES. This is the old, let's say, complex of the laboratory. This building here is the building in which the core, the heart of SPES is located. SPES is based by the fission of uranium target, direct fission with a proton beam delivered by a cyclotron, 40 MeV neutrons, 200 microamps, and then we basically we will deliver beams by the fission of uranium carbide, but it's also possible also to deliver a light beam like aluminum 26 if you replace the uranium carbide with the silicon carbide. Okay, so this is a very quick view of laboratories, and what I will describe in the next is the work mainly done at this facility, and also I will present some perspective with these radioactive beams. Okay, so the cluster structures in nuclei is a very old idea. Is at the end of 60 when Ikeda suggested that the states in nuclei can be based on alpha particles because they are the strongest particle bound. So as you can see here is the helium-4 is the most bounded nucleus, and also possible cluster structure can be found in carbon-12, oxygen-16, neon-20 because they can be structured as alpha particles. And this the basic idea is that this cluster structure appear just at the onset of the particle decay. Okay, so later on there was an extension of this idea of the cluster of alpha particle cluster in nuclei. Basically, in neutron-rich nuclei, you can think of neutrons like valence particle to yes.
We're not able to see your slides now.
So actually, somebody in between interrupted. So you have to pin on
Just pin, it will come.
instead of presentation. then it will come. So you
Okay.
go to the participants, and there you find Marco, then presentation. There you have to pin.
Okay.
Request everyone who is facing
Okay,
forward.
okay.
So
Okay.
no, you go ahead. It was all right. I was talking. Okay. Yeah, fine.
Okay.
Yes.
Okay, so the idea of this extended IKEDA diagram is that in neutron-rich nuclei, the neutrons act like a valence particle between the clusters. This is in practice like like the orbitals, the valence orbitals in atoms, and there are some calculations, for instance, here in the with the antisymmetrized nuclear dynamics that show some structure in, for instance, in the beryllium nuclei, in charge and in neutrons. And there is also the idea that at 3' clustering might be the preferred structural mode. And the valence neutrons stabilize the unstable multi-cluster states. This could be investigated using also radioactive beams. There is another way to look to the cluster. Let's say in the pre-equilibrium emission of nuclei. Pre-equilibrium emission means that when when a target and a projectile collides in central collision, there will be, before thermalization, some pre-equilibrium emission, some fast emission, and then the statistical decay of the compound nucleus. In this picture, the cluster formation can be either preformed in the sense that that is the projectile can have a cluster structure, an internal cluster structure, or a dynamical formation due to coalescence of nucleons during the course of the reaction. This evidence, of course, is very old, because here I reported, for instance, a very old measurements done at the Texas A&M University with a cyclotron, in which, as you can see, a beam of cysteine oxygen at very high bombarding energy, 27 MeV per nucleon, hit a samarium target. And when you look to the spectra at a very forward angle, you have a very strong production of an alpha particle that is coming not from CN, from the emission of the compound nucleus. So this can be ascribed to pre-equilibrium, some incomplete fusion, or so on. But you can see if you look to the spectra coming from a pure statistical decay, so that the alpha spectra in different reaction channels, they superimpose perfectly. So this emission appear at very forward angle. But also with Garfield, we observe a similar evidence comparing nickel plus zinc reaction with oxygen 16 plus tin 116 reaction. As you can see, also here with the oxygen beam at the forward angle, you see these are in the range of 45 degrees, and this is about 30 degrees in the laboratory angles. You see that again there is an extra production of very fast alpha particles. that can be due to the projectile backup, and so these motivate us in study the further study this emission, and in collaboration with some Russian theoretician, in particular Olga Fotina from Moscow, we developed an hybrid model, a pre-equilibrium model, in which you can put the normal hybrid Exciton model by Griffin that describe the pre-equilibrium emission, but also a possibility to put by hand, let's say, a mixing of alpha configuration. For instance, in oxygen, you can consider an oxygen cysteine or an oxygen cysteine composed by carbon 12 plus alpha particle. And then mixing this, you can try to reproduce your experimental spectrum. For instance, here, this is a first attempt to reproduce our spectra from oxygen cysteine. As you can see, if you consider protons, there is no need to put alpha cluster preformation in this model, and the experimental protons are more or less reproduced without any cluster assumption. This is not the case with alpha particles, but in any case, also this model does not account for the experimental spectra, because you saw that also if you assume a 50% of alpha cluster preformation, again, this is a very strong assumption, you do not you do not reproduce the spectra. So there is let's say a problem in understanding this emission also with the model, because there is no today a model that can account for this. So for this, we have performed a new experimental campaign in our apparatus. That is the Garfield plus LCO array for charged particles. As you can see, Garfield is two drift chambers, double stage delta E, based on microstrip gas counter plus cesium iodide, that covers the angular from 29 up to more or less 150, so these are segmented. And in the forward direction, there is this RCO counter, that is a three-stage telescope based on ionization chamber, 8 sector, silicon strip, 8 sector divided in 8 strip, and then cesium iodide. And you can, with high granularity, perform Z and A identification. So in this way, you have a very performing setup in which you can do correlation and a complete reconstruction of the event of the nuclear reaction. So I will focus mainly on two different campaigns. One is related directly to the fusion reaction in light nuclei using carbon, oxygen, and nitrogen beam on very light target, and another in fusion reaction, but at the onset of equilibrium. So because what we want to do is just to let's say made an excitation function of all the bombarding energy regime, just to see if there is a change in the emission, and to study the evolution of the emission. So just to understand in some more complete way the behavior of the interplay between fusion and equilibrium. Okay, let's focus in the first part, in the fusion reaction in light nuclei. As you can see here, there is the example of the carbon-on-carbon reaction at 95 MeV. And you can see here is the a bidimensional plot of the total collected charge in the event and the transversal and the momentum and the z momentum of the beam. And here you can see different loci to identify, for instance, central collision. These are the complete events in which the evaporation residues are detected, and so you can study the de-excitation of the compound nucleus magnesium 24. And then the peripheral collision, in which you can see the excited states of carbon 12, and also incomplete events in which you have no evaporation residue detected. Okay, if we concentrate on the complete event, on the statistical decay of magnesium 24, you can see if you have these are the protons and these are the alpha spectra in coincidence with different residues, and what you see is that a statistical model analysis. This is an analysis of a developed in-house statistical model based on the Hauser-Feshbach approach, in which also discrete levels of the light nuclei are included. You can see that basically the spectra are well described, with the exception for the alpha particles in coincidence with oxygen, for instance, here, and neon. And if you and if you look also to the branching ratio of the different channel, experimental and simulated, in which the residue is populated via the emission of the maximum of alpha particle that can be emitted in this channel, you see that basically experimentally, and this is the difference between the experimental and the simulated reaction, basically experimentally you have a preferential emission of alpha particles. So the alpha particle is preferential emission, so this can be a signature of the residual alpha structure correlation in this excited nucleus. If we look also to the alpha-alpha kinematical correlation, for instance, in the carbon plus carbon case, if you introduce the Jacobi coordinates between between the two alpha particle emission and the emitted core, and then you look in the Q value spectrum, you see this is the pure oxygen. This is the 2 alpha channel. So this is the pure 2 alpha channel emitted, and then you see here at higher Q value you have a very broad peak, and this is let's say this is due to the emission of a neutron that is undetected in our case. And so if you plot the cosinus of the Jacobi coordinates and the energy correlation between the alpha particles, you see that you have a distribution that can be put in correlation with the hierarchy of the emission of the alpha. For instance, here, as you can see, you have a preferentially the alpha is emitted before, so the neutron is the last particle that's emitted. So alpha particle correlation indicates a sequential process with a clear hierarchy in the emission sequence. So this is again a signature of some particular structure of the alpha particle. And this is also confirmed in the carbon-12 to carbon-13 case, in which with the same philosophy, you see that here in this plot here, you have the experimental distribution in black, and then the distribution related to the emission of the first chance, second chance, and first chance emission as it comes from the model. If you do a refitting procedure and you assign different the ways that fit the experimental spectrum, you see that after the fit, you have an inverted hierarchy of the emission of the neutrons, that, and the neutron is emitted with high probability as a third particles. Again, in this set of data, we can also study the Hall state in carbon-12. The Hall state is a very interesting and important state for the burning of star, and there are many. There are basically two different ways in which the carbon-12 decay. In 3 alpha, with a sequential emission through a beryllium-8 doorway, or a direct emission of 3 alpha particles. And again, if you look to the peripheral collision or to the central collision, and you do the Dielis plot reconstructing the energy of the 3 alpha particles that you detect, you see that again, comparing the experimental and the calculation, you see that negligible contribution of the carbon-12 in 3 alpha is observed, while basically all the data are compatible with sequential decay. Okay, so this can be also studied if you look to a fragmentation reaction. This is a campaign that has been pursued at the Laboratorio Nazionale del Sud in Catania with FAZZIA. FAZZIA is an array of state-of-the-art silicon cesium telescope for the reconstruction of Z and A in charge of particles. And if you study the fragmentation reaction of neon and sulfur beam at very high energy, like 25 and 50 MeV per nucleon in a carbon target, you can explore the excitation of the carbon as a function of its kinetic energy, and then you can also reconstruct the excitation and to see the contribution of the decay in 3 alpha particles by direct or sequential contribution. These are preliminary results, but as you can see, you can consider again sequential decay, linear configuration of phase transition exploration. Of course, this can be with set of data. We can study evolution with the carbon-12 kinetic energy, and also simulation are needed for the different decay paths. This is just to see if the carbon populated in different way, in different reaction, in different condition, can have different decay in 3 alphas. And with this set of data, it is possible by the correlation of oxygen, for instance, also other particles like oxygen plus alpha, beryllium or lithium, also to explore the interplay between structure and dynamics in the fragmentation. Okay. So this is our first part. The second part is the fusion reaction at the onset of the equilibrium. You see here again, we compare different 4 different reactions at same bombarding energy, except one in which the titanium 46, that is the common compound nucleus, is formed at the same excitation energy of this reaction, just to compare, just to have an idea of the role of the excitation energy. And then here again we can select the complete events in which the total charge is detected and also the total momentum is detected. And you can see here in this plot in which you have the charge and the energy of the detected particle. You see the different loci in which the different reaction mechanisms are located. You are interested in this part here, and you can see here also the silicon 30 was also spoiled by oxygen, but with the help of simulation, we can get rid of this contamination. And then at the end, if you compare the experimental data and the Gemini++ simulation, you see that our selection is good enough to proceed with the simulation, with the comparison with the data. As you can see here, the experimental charge distribution, especially for residues, is compared with the 3 reaction. And you can see here this the excitation energy of the nucleus that is increasing in this way. And you see that for higher excitation energy, the reaction chains are longer, and so the lighter fragments are more populated with respect to lower excitation energy. And if you compare the 2 reactions with the same excitation energy, you see that the 2 distributions are superimposing. This means that in practice you have a statistical decay. And this is also confirmed, for instance, by the comparison with the Gemini++ statistical model calculation that reproduced fairly well the overall residue distribution. But if you go into more detail, and if we take the ratio of the experimental to the simulated, to the predicted part, the yield of the particle as a function of the angles, you see that the alpha particle yields are well reproduced, or fairly well reproduced, in the backward part, but not at all in the forward part. And this is overestimated also by a factor of 10, depending on the entrance channel. So this behavior has to be understood in a complete way. So we are trying to understand this, which is at what it could be attributed. And then if you look to the protons, you see that in this case there is a general underestimation. There is a general overestimation of the calculation with respect to the experimental. And if we look to the distribution of the yield residue by residue, we see that for the heavier residue, you see that the alpha are always overproducted in the experimental part. And also if you look to the very forward angles, all the heavier, all the alphas in coincidence with the heavier fragments are overproducted. There is an overproduction of alpha particle in the experiment with respect to the simulation. If we go in more detail, and if you look to the like in the case of carbon on carbon, the difference in the branching ratio of the different channels associated with, for instance, the production of calcium, you see here where you produce the calcium, you can produce calcium via the emission of 2 protons plus neutrons that here are not undetected, so we are not putting the neutron here, or the calcium plus 1 alpha particles. And if you see here, there is again a staggering, an even odd effect. And also, if you look to the even residue, you see that if you compare the branching ratio experimental and calculated, you see that the extra production of alpha particle is compensated in the calculation by the overproduction of the proton. So this means that experimentally the emission of the alpha is favored with respect to the emission of two protons. This is true also for the argon channel. You see, this is the maximum alpha channel produced, and this is the alpha, 1 alpha plus 2 protons. And again, the two experimental and calculated are compensating. But if you go, for instance, to the sulfur case, in this case, you see that these two channels are not really compensated, but with longer alpha chain in the calculation appear the emission of light fragments like beryllium or boron that are not accounted for by the experiment. And this is more evident here, for instance, in the silicons, in which in practical the competing channel with the 4 alpha particles is the emission of a boron fragments. So this, of course, has to be understood, which is the origin of this behavior. But if you look, so the message is that also if the overall features seems to be more or less reproduced, but if you look to the details of the cascade, you find very big deviation from the simulation. Again, I would like to mention also another reaction that we have studied, the oxygen plus the oxygen plus Q and the fluorine on nickel that populates the same rubidium 81 nucleus. So this is a mass region that is twice of the previous one. And then here, if you look to the emission, to the experimental emission, and the Gemini plus prediction, and then you see the difference. The difference can be ascribed to the pre-equilibrium emission. These are alpha energy spectra in the at-forward angles. And then if you compare these two differences in the two channels, you see that for the fluorine beam, the pre-equilibrium components is more enhanced with respect to the oxygen beam, and this is in agreement with some systematics of alpha Q value on effect of the incomplete fusion on the projectile structure, because if you have alpha particle less bound, you have a stronger contribution of this pre-equilibrium, incomplete fusion, or breakup, or whatever contribution in your experimental spectra. And looking back to the past, you realize that this was observed also many years ago. Sorry? And also here you see that there is a strong contribution of fluorine beam at the energy near the beam, also at very low bombarding energy. Okay, so what is the future of this study? So we can go to study the equilibrium with the space beam, in for instance in reverse kinematic using Kin 132 beams on aluminum 27 or on silicon target, and also on rubidium on silicon target. And so different projectile target combination allow for a direct comparison of the observable, also with respect to what I mentioned before of this cluster structure in neutron-rich nuclei. And for this one, you can these are reverse kinematic reactions, so the RCO will be a good tool to study this reaction. You can also think to have a higher granularity, lower threshold, or heavy Z identification, and we can also think to use adapted Fazia modules to make the particle correlation, and also to include the neutron detection. As far as the decay of light nuclei, we can study, for instance, the reaction with beryllium isotopes beam, like beryllium-7 and beryllium-10 on carbon. The unstable beryllium nuclei can be produced with this reaction space using this target, the boron carbide. And then we can compare this with the reaction with stable beam. And this is a very preliminary calculation of statistical model calculation, saying that a strong signal will be in the neon 19 as far as is regarding the emission of the alpha particles. Okay, so I will come here to my conclusion and many open questions, because I show you an extensive experimental campaign that is in progress at Legnaro with the Garfield plus encounter array for charged particles, in which we select the charged particle correlation in selected decay path of excited system that shows significant deviation from a pure statistical approach, especially, as I shown, in multiple alpha decay chains. And pre-equilibrium emission from excited system formed with different entrance channel is ongoing. So study, I forgot, the study of the pre-equilibrium emission is ongoing in these two mass regions. And then these are the question that is open. Effects of cluster structure in nuclei can be really deduced in a quantitative way in this with this experiment. Steps can be given answers, and of course we need new inputs for more complete theoretical models. And then just to show, this is the nuclear collaboration, but I want to finish my talk with happy birthday to Dr. Nayak. These are our a list of our joint papers and the view of the different detectors we have used for our collaboration. So thank you very much, and that's all.
Thank you, Professor Marco, for such an excellent talk. You have showed very nicely all the facilities of your lab and covering broad topics One is that of the competition between non-equilibrium procession and fusion fission. At the same time, also have solved the cluster structure and specifically that of Hoyle state decay. And I have a question on this Hoyle state decay that you have
Mhm.
showed the result that DDL decay type
Mhm.
that limit given something like 1 plus minus 0.8%.
Yes.
Is
Mhm.
it that much, or I think it is much lower in the latest
But
development?
no, it depends. So I think that also let's say the contribution of this direct decay, it's really a debating question because as you can see, in this in direct reactions and also in this in this central collision that we have explored, the contribution is very small. Also smaller because in fact, we find someone that is too much probably. But in any case, if you look to the data of fragmentation reaction, like the data of Raduca, for instance, and I think they have been, the experiments have been performed with the Chimera array in Catania, they found up to 20%, up to 17% of this direct decay. That is very high. I think that some more answers or more insight can be given by this Fazia-Core experiment that is ongoing of analysis because there is a very nice opportunity to explore all many regime and many beams and many space of phase of the production of carbon. So I think that in this way we can.
Yeah, in one of your experiment involving 20 neon, that decay, you have tried to see the coincidence between different outgoing particles with alpha and try to
Yeah.
find out the linear chain combination. Is it right?
Okay, let's say, yeah, so there is one thing is to see the correlation of 3 alpha particles, to see just the OH state. And then you can see the correlation between, for instance, oxygen on the alpha particle, lithium of alpha particle, just to see other, let's say, unbound states in light nuclei. So these are two different, let's say, things. If I understood correctly, because I'm not, because I'm not really into the detail of this work that is analyzed by the French people in Ganil.
Okay. Okay, I think we'll go over to the other questions by any other audience. They can unmute themselves and start asking question one by one. Any question, please? If not, then let us thank the speaker once again for his nice and excellent presentation. Thank you once again. Yeah.
Thank you.
So we'll go over to the last presentation, the third presentation, and this will be by Vishal Desai. Dr. Vishal Desai is a student of Dr. B.K. Nayak, and he is the luckiest among all the students because he is the only full-fledged student of Dr. B.K. Nayak, and he has in fact completed his PhD from Nuclear Physics Division, VRC, under the guidance of Dr. Nayak. He was a postdoctoral researcher at Oregon State University, USA, His research interest includes neutron-induced fission, multi-nucleon transfer. Currently, he is working as a postdoctoral researcher at Tata Institute of Fundamental Research, Mumbai. So today he will speak on determination of first neutron-induced fission cross-sections of unstable nuclei via surrogate reaction method. So may I now request Vishal to give his presentation.
Good evening to all. I hope I'm audible to all of you.
Yes, yes, you are.
Thank you, sir, and thank you, sir, for the introduction. And let me go to my slides. Okay. The slides are visible.
You have to make it bigger in
Okay.
presentation mode, and then
Okay,
hide,
I think.
then hide that pop-up.
Okay. Okay, I think this is okay.
Yeah.
So, good evening to all. It is my pleasure to being a part of this webinar series on contemporary topics in nuclear physics. I thank a lot to the organizers for giving me this opportunity to speak here. It is also an occasion of 60th birthday of Dr. B.K. Nayak, with head nuclear physics division, and also my PhD guide. I had a good fortune of working with him closely as a PhD student. During my PhD, under his, is there okay everything, or am I audible? During my PhD under his guidance, we carried out some measurements, such as we measured the prompt fission neutron spectra in neutron-induced fission. We also measured the neutron-induced fission cross sections for some of the unstable nuclei by using surrogate methods, which is also a topic of this presentation. I also got the chance to work closely on neutron detector instrumentation and setting a neutron detector array, etc. So as I told in the today's presentation, I'll be talking about our measurement on determining neutron-induced fission cross-sections of unstable nuclei via surrogate reaction methods. So in this talk, I will, initial part of my talk, I will introduce the topics. So we'll see how these neutron-induced cross-sections are, why these cross-sections are important. Then we will learn about the surrogate reaction method and its application in real-life measurements. Then I will present our measurement on determining neutron-induced reaction cross-sections for some of the nuclei. I will present our results in briefly, and finally I will conclude my talk. So the reactions of neutrons with the nuclei across the isotopic chart, taking place at a few kilo electron volt to the tens of mega electron volt, are important for several reasons. These cross-sections are important in astrophysics, its applications in nuclear energy, and as well as national security. In astrophysics, these cross-sections are key input parameters for modeling the nuclear synthesis via slow and rapid neutron capture processes. These cross-sections are important in nuclear energy applications. We will see briefly how these cross-sections are important in nuclear energy applications. So, according to the latest report by IAEA, there are 450 nuclear reactors are in operational. Most of these reactors use, for their operation, they use thermal neutron. And from these reactors, some hazardous type of radioactive waste will be generated. So that waste contains the fission product as well as some minor actinides. Here, the chart on right side here, one can see how the minor actinides will be produced in the reactor, and they form actually a nuclear waste. So, and to get rid of this nuclear waste, two strategies have been applied. one is incineration and the storage at some ecological site. So here the term incineration means the changing this or the transmutation of these minor actinides into some less radioactive species. So for that, so this can be achieved by making them fission in some dedicated reactors, and for that the efforts are being taken to construct the reactor, which is based on fast neutrons. Also, also there are some efforts are being taken to construct the reactors which will use the innovative fuel cycles like the thorium and uranium cycles. But for the realization of this all effort, what we need is the basic neutron-induced cross-section data that may include the fission cross-section, the capture cross-section, or N2N, etc. These cross-sections are important. But remember, we want cross-sections for the minor actinides. So how to measure this data? Because these minor actinides are short-lived or they are radioactive. So direct measurements with these targets or these minor actinides using a neutron as a beam are not possible, as they are short-lived or they are unable to serve as a target. Even in the well-equipped laboratory, we cannot produce those targets. Also, the getting the neutron beam of required energy is also is not easily accessible sometimes. So doing this experiment is sometimes even challenging during the RIBs also. So in this situation, the only the solution is to use some indirect method. And there are some indirect methods has been used in past, like this ANC or asymptotic normalization coefficient, Coulomb dissociation, or the Trojan horse method. These all methods have been used in astrophysics, physics, and there is the different approach, slightly different approach from this method. From these methods is surrogate reaction method. This work for the compound nuclear reaction, basically when there is a slow time scale is involved. So we will see what is surrogate reaction method is. So as I told, the surrogate reaction method approach is an indirect method to determine the cross sections for compound nuclear reactions, and this method can be used when the actual measurements are highly impossible. So we'll see what is surrogate reaction method here. So to understand the surrogate method, let us consider a design reaction, neutron-induced reaction, for which we want to measure a cross section, maybe fission or a particle fission cross section. So neutron combines with a target which is radioactive or say minor actinide. This combines with the target A and forms a compound nucleus B star, which then undergo fission or other kind of decay. So for this desired reaction, we can write the cross section. Say for the fission cross section, we can write as we can split this into two parts: the compound nuclear formation cross sections and the decay part. So, but since this target is not available, we cannot perform this experiment in laboratory. So in that case, what we can do is we can use a surrogate reaction, where one can use a stable projectile and stable target to produce a same compound nucleus B star. And if these compound nucleus, two compound nucleus are at same excitation energy, then decay channels will be identical. This is what Bohr hypothesis tells us. If once the compound nucleus is formed, it forgets its history. I mean, what way it was formed. So if their excitation energies are same, then their decays will be identical. So one can measure the decays from the surrogate reaction and put those decays in this formula to get the cross section for required cross section for the required reaction. So this is how the surrogate reaction helps us to determine the cross section for desired reaction using a surrogate reaction. So, so as I told, we can determine these decay probabilities from surrogate reaction, and this compound nuclear formation cross sections we can calculate using the suitable optical potentials. There is another approach called as the surrogate ratio method, where the cross section for the desired reactions are determined with reference to some reference reaction whose cross section is known. So this ratio is equals to the ratio of compound nuclear formation cross section for these two reactions and the ratio of their decay probabilities. So similar to the what I explained earlier, these decay probabilities are inferred from the surrogate reactions and putting them here. This compound nuclear formation cross section can be inferred from the calculations. So one can get this ratio, and knowing this cross section, so finally one can get the cross section for desired reactions. So surrogate reaction method is very successful in determining the fission cross section. There are so many measurements have been done in past. I have shown here some examples which tells you the story how this method is successful in applying, how this method is successful in applying it to the determining fission cross sections. So but there's one thing common in all this measurement is they use light ion, like they use proton. In some measurement they have used proton induced surrogate reactions or deuteron or alpha induced reactions. Yeah, Dr. B.K. Nayak used this method first time in India to determine the cross sections for neutron induced fission cross section for 233 protactinium. He used the surrogate ratio method in slightly different approach. I will tell you how his approach is different than the usual surrogate ratio method. But he measures this neutron induced fission cross section for 233 protactinium with reference to the lone cross sections for this N plus 235 uranium reaction. And by knowing, and then he measures the decay probabilities using the surrogate measurement to get the cross section for the required N plus 233 protactinium. So how his approach is different than the usual surrogate ratio method? First of all, he used a 6 lithium induced reaction, 6 lithium as a beam, which is considered to be a heavy ion, and then he used a 232 thorium target. So we know that 6 lithium, when we use the 6 lithium as a beam, we have transport channels. So when the deuteron is pairing with target and alpha is coming out, then the compound nucleus that we will form is a 234 protactinium. And in other way, when alpha is fusing with target and when deuteron is coming out, in that case 236 will be the compound nucleus. So what in a surrogate ratio method which I shown here earlier, one has to perform two surrogate experiment, one for desired reaction and one for reference reaction. But in his approach, he is producing the two compound nucleus in the same reactions using these two transfer channels. So the two compound nucleus will be produced in situ in the same reaction. So it has the advantages over the usual surrogate ratio method, that we can eliminate the uncertainties arising due to the beam fluctuations as well as some target thickness. So he measured these cross sections using this, and later on this method is known as hybrid surrogate ratio method. So he measured these cross sections, 233 protactinium NF cross sections, these black points are his measurement, and these are some previous measurement reported measurement reported earlier. So from this chart from on the left hand side, one can understand how these cross sections are important in a thorium uranium when we talk about thorium uranium cycle. So we can see starting from 232 thorium that this 233 protactinium is formed right there in this highlighted box just before this 233 uranium formation. So this 233 protactinium is basically has a half-life of 27 days, and so the inventory of this 233 uranium will be decided by this particular isotope. So knowing the fission cross sections for this isotope in relation with their cross section, one can predict the amount of 233 uranium present in the reactor. So in a continuation of this method, we measured the cross section for 241 plutonium NF reaction. So this 241 plutonium is also another important isotope for the in a nuclear reactors. And when we thought to measure this cross section, this was the situation. Here I have shown. So these open circles are the earlier reported data. So this measurement was done in a direct experiment by Lawson-Moss group. They use a Spanish neutron source for this measurement. And when these measurements were compared with the available standard libraries, that time the discrepancies between these two data up to 30% was found. Discrepancies up to 30% was found between these two data. And the source for this discrepancy was not known because as you see, this 241 plutonium is radioactive. It also continues to decay while measurement also. But author claims that this decay was corrected while measuring this cross section. So and we know this 241 plutonium is important nucleus. It was suggested to carry out some further confirmatory measurement. So in surrogate method, we don't use the direct neutron or direct this target. So we thought, or this actual target. So we thought it's good to use the surrogate method to determine this cross section. So for this experiment, we use a simple experimental setup. We use a 6-7 lithium beam, which was obtained from the Peloton accelerator at VIFR. And then we use 230 uranium and 232 thorium targets. Then we use 2 delta E telescopes to detect the projectile-like fragments, and 1 large area solid-state detectors to detect the fission fragments. So here is some plots that shows the particle identification plot, where this proton, deuteron, tritron, etc. are well separated from each other, and this is the fission fragment spectra. So for this measurement, we use 6 lithium as a beam, and so for the desired reaction, that is N plus 241 plutonium is our desired reaction. So for this, we use these surrogate reactions where we use 6 lithium as a target, 6 lithium as a beam and 238 uranium as a target. And when alpha fused with target, it forms a 242 plutonium, which is a surrogate for our desired reaction. And then we use a reference a reaction which is N plus 235 uranium, and for that we use this surrogate reaction. that is 230 thorium target we use, and 6 lithium deep tritinyl we use to produce 236 uranium compound nucleus, which is surrogate of N plus 235. So, and here on right hand side, this is the excitation energy spectra. This upper channel is gated with deuteron and fission, and the lower channel is it's single deuteron. So when we get the spectra with deuteron and fission, so that means, so okay, so in the lower channel, when we get the this single deuteron gated excitation energy spectra means, so deuteron is coming out, that means alpha has fused with the target, so that many number of compound nucleus we are forming, and when we get the excitation energy spectra by deuteron and fission, that means that many compound nucleus under one fission. So basically this this ratio will give you the decay probability. So the compound nuclei that undergone fission to the compound nuclei that were formed, so that will give the decay probabilities. So we extracted the decay probabilities from this surrogate experiment, and then we use that surrogate cross-section formula to get the neutron distribution cross-section for 241 plutonium. Here are the cross-section that we inferred from our surrogate measurement. So these red points are in our measurement, and they are very well in agreement with the previously reported data. And this dotted line here is the standard library that I shown earlier in plot. So basically, so we can conclude that there was some error in predicting the cross sections. So we then used the Empire code to calculate these cross sections. We used various input libraries, and so this dotted line here is the Empire calculations using the Riffle tree, which is good in agreement, but there are discrepancies at certain region. So we then tune the fission barriers a little bit, and then we got this best fit here. This red line dot is our best fit to this data. Then in another experiment, we have determined the neutron distribution cross-section for this 239 neptunium and 240 neptunium. These nucleus are also formed in the reactors, and on the path to the formation of heavier mass element, and therefore the fusion cross-section for these nuclei is also important in terms of this polymerization and resistance aspect of the reactor design. So again, these two nuclei are short-lived, so the direct measurements are not possible. So we use surrogate ratio method to determine the cross section for this nuclei. And so here are the details that we use these surrogate reactions for the desired reaction, and this is for the reference reaction. And here I have shown these cross sections here, and along with some calculations using Empire code, and also data with some library. And here are the cross sections for 240 neptunium. In another experiment, we have also determined the cross section for this 234 protactinium NF reaction. We use hybrid surrogate ratio method for this measurement. We use 232 as the target and 7 lithium induced reactions as a surrogate reactions. And these are the cross sections, and these cross sections are in good agreement with the Empire calculations, as shown here. So far we have seen that the surrogate ratio method has been extensively used to determine the neutron-induced fission reaction. But as we have learned, that surrogate reaction method is very general and that can be applied to any compound nuclear reactions. But so far no attempts were made to determine the compound nuclear cross sections involving like reactions like NP or N alpha. So recently we have measured the this proton emission cross sections in Fe55 neutron induced reaction. So I will show the details of this measurement on next slide. So this Fe55 nucleus is very important in our fusion reactors technology. So we know that in fusion reactors, the structural material they use is a stainless steel, so which has a composition of chromium or nickel, etc. And in the fusion reactors, we have a very high energy neutron. So the reactions of this neutron with the structural material can produce any kind of nuclear reactions with the structural material because the energy of this neutron is very high. So any kind of nuclear reaction is possible with the structural material, and because of this, the many radionuclide will be produced in the reactors. So Fe55 is one of them. This Fe55 has a large cross section for the proton emission. When this Fe55 interact with the neutron, it has large cross section for the proton emission. So proton means it is a gas, so it will always try to come out from the structural material. That may lead to the swelling in the structural material. Basically, it will damage your structural material. So therefore, these cross sections are important. And again, this is a radionuclide, so the direct measurement was not possible with this target. So we used the surrogate ratio method for this. We used 52 chromium 6 lithium D as reaction as a surrogate for this required 55 NP reaction, and the reference reaction is this. We use 45 scandium 6 lithium alpha as a reference reaction, and here are the cross sections that we inferred from this measurement, which are agreement with the empire calculation as well as this this Rosmond library. So other libraries like Tyndall's phase data. So recently, then this another group from BHS, Ramandeep Gandhi et al. Has determined the this proton emission cross section for another radionuclide, 53 manganese, and here are the details of their measurement. This diagram here shows how the 53 manganese will be produced in the these fusion reactors, and here are their details of their experiment, the surrogate reaction method for the desired reaction and the reference reaction, and these are their measurements along with some library predictions. And there's another measurement on 59 nickel NXP, that's a proton emission cross section by Jyoti Pandey et al. So they use 56 lithium D to form this 60 nickel, which is actually the surrogate for this 59 nickel NP reaction, and this is the reference reaction, and here are their measurements along with some libraries. So finally, I will conclude here. So as I said, this surrogate nuclear reaction is a program to develop it combines the theoretical and experimental aspect to determine the cross section for the reactions involving unstable nuclei. So I shown the the measurements to determine which are aiming to determine the neutron diffusion cross section for some of the isotopes, minor actinides. I also shown the results for this neutron induced particle emission cross section. That is, we talked about proton emission cross sections using this surrogate ratio method, and this measurement actually shows that we can use this heavy ion induced reactions effectively, or even the heavy ion induced reactions are successful as a surrogate reaction for measuring the cross sections. And we know that nuclear physics is moving towards the RIVs, but there are some measurements that are not possible even using these facilities. So I feel the surrogate ratio method is, still have become a good technique to determine the cross sections. So finally, I thanks a lot. Thanks to all of you. I thank all my collaborators from BRC, and thanks a lot.
Thank you, Vishal, for such a nice presentation. We have learned from your talk how important this surrogate reaction is, and by using the surrogate reaction, how one can measure the capture cross section, neutron capture cross section for involving the radioactive targets. Also, one can study about the structural properties, the modification of structural properties in case properties of the materials of reactors, and also how important it is in incineration of the materials or products, radioactive products. So thank you once again, and the session is open for questions and discussions. The audience can unmute themselves and start asking questions one by one.
Hello, can I ask? I'm Ramchan from BRC.
Yes, Ram.
Okay. So Vishal, so apart from this 6 and 7 lithium and lighter projectiles, is there any attempts on the heavier ions like alpha cluster nuclei for this kind of surrogate reactions?
Other heavier nuclei like
Other than this 6-7 lithium and these kind of lighter nuclei, there are other kind like this alpha cluster nuclei, which is which may be able to transfer even heavier heavy ion transfer kind of thing. So, is there any kind of such measurements to do these surrogate reaction studies?
I mean, so far such studies have not been done. We know that. I mean, we know that there will be a difference between the J-pi state that we populate. So I think till date, some lighter nuclei and 6 lithium, 6-7 lithium has been used, but so far no attempt has been used using heavier than that, like barium or others. I don't know if this if it is possible or not.
Okay, thank you.
Can I ask a question? I am Rajiv Kumar here from Director of Physics and Division.
Yes.
As Dr. Vishal told that no effort has been done using the N-alpha cross-section using surrogate reactions far. So what are the changes in measurement of N-alpha cross-section? Why it has not been done so far?
I think N-alpha can be done if you have if we have a suitable target for the surrogate measurement. Then N-alpha can be done. N-alpha or N-gamma measurements can be done.
Okay. Thank you.
Can I make a comment? Can I make a comment?
Yes, sir.
Vishal, There is one student from Calicut University, Mithun Neelakantan. He is studying N-alpha reaction for copper 62. So he recently completed the study and the paper is Dr. Nayak. So N-alpha reactions can be done, but it is a bit more complicated using a surrogate method. Thank you.
Okay.
Actually, so Dr. Suryanarayan, that's what I'm asking, why it is a bit complicated doing N-alpha.
Because you have to say the surrogate reaction is for N-alpha, you have to choose a normalizing reaction also is similar to N-alpha, which will be difficult. If you use NP,
That's what I mean. That's what I want. I mean, if we need a suitable target, I mean,
the free equilibrium and the direct reaction components will be different in normalized reactions. Desired reactions are not same. The equilibrium components and the direct reaction components will be very different. It's difficult to get a correct reaction.
okay.
Okay, thank you.
Any other question?
There is a question in the text form. Would you like to answer that?
Yeah, you can read that.
Prajapati asking that question is, there may be chance of direct transfer of breakup components alpha or deuteron from lithium 6 to target in 6 lithium plus 238 uranium reaction. Would you like to comment on this?
Okay.
But
I mean,
okay, who is here? She can just explain that. Actually, you know this. Your reaction is very much depending on the transfer. So yeah, you can respond to.
So what I get is she's talking about that when we have a lithium beam, so there are other transfer channels are also possible, like tritium or something like that, tritium and alpha or something. I didn't get the question actually.
Is there? Yeah, here it is. Yeah, can you read this?
Okay,
There may be
chance of direct transfer of breakup components.
What you can do is to explain to the questioner regarding this question. Maybe she has or he has not fully get your from your slide. So you can just explain it.
Okay. So we actually when we use 6 lithium, we use this alpha and deuteron transfer channels, no, to populate the compound nucleus.
Yeah, actually, maybe I can comment on this. Actually, that transfer or the incomplete fusion, there will be no difference in this case. So, whatever that 6 lithium, whether it breaks up into alpha and D, and then one of the fragments get fused with the target, or the alpha is directly transferred to that, it will form the same compound nucleus or residual nucleus, which we will not be able to distinguish. That is what we do. So there will be no distinction. So it will, both are considered together.
Yes.
Is there any question from YouTube side, Sanat?
Yes, there is a question from Gopal Mukherjee.
Yes.
Gopal is asking that is it the same excitation energy as well as this neutron induced?
Yes, it will be the same excitation.
Yes, it should be.
I think this is the point only. No, you just
yes,
do the measurements and it will be same.
Yes, it has to. Yeah. Any other question from YouTube?
No.
Okay. Okay. If there are no other questions, then let us thank the speaker once again and thank all the speakers of today, and also thank all the participants, both from Gmeet as well as YouTube. Thank you. And just to inform you that the talk is being recorded and it will be saved in YouTube. So if in case somebody has missed, he can take it again in YouTube. You can search for these contemporary topics in nuclear physics in the name of different dates of 24th June, 25th June, and 26th June, and then you'll be able to find out. So thank you once again, and you can leave the meeting. Yeah. Yes.
Hello?
Yes, Kripa. Yes.
Yes, Kippada, you
Yes,
can try
Kripa.
now.
Actually, I just wanted to try now if others have left, you know.
Yeah, you can wait for some time. You can wait for some time. Kripa.
Kippada, Kippada, please
wait
switch
for
your
some time.
Okay. Just a moment.
Yeah, wait for some 5-10 minutes. 5 minutes at least. Yes, of course.